So yesterday, just remember we saw some basics and we end up with a brief tutorial on the tools we have to analyze our data. And we stopped at a point looking at our association matrix as the basic information, the raw data we're going to use to explore the social patterns. So today what we have here is we're going to start with hypothesis testing. So looking at that matrix to see if there's any patterns in it, or essentially testing the null hypothesis that associations occur at random. So individuals will associate or form groups with whoever they want, and we want to test if that's the case or not. And then later on this morning, we're going to start using some multivariate techniques to visualize these matrix, essentially looking for this, the same thing. So if we reject that hypothesis, how our association matrix looks like. And then we're going to finish today with trying to model these association matrix using hierarchical clustering analysis. Good. So now for the first lecture, we're gonna look into permutation tests to test for random associations, and then I'm gonna present for you guys two concepts of social differentiation and social representation really quickly, because these are the raw information we need to test how much statistical power we have to for our permutation test. Right, so that's how we stopped yesterday for those who skipped class yesterday.
The beats.
I'm going to give you some homework later.
Yeah.
So essentially what this means here, we have individuals in the rows and the columns, and the values here are the association index, so the proportion of times individuals were seen together in the group. We talked a little bit yesterday about associations. So being in the group is the requirement is the context that we need for individuals to perform their social interactions. So that's one assumption. And then collecting the individual's ID, their identifications over time in groups, we can measure the proportion of times two individuals were seen together. And here in the diagonal, we have the interaction, the individual with himself, so it will always be one, and we're not going to look at this. And this index, it varies from 0, never seen together, to 1, always seen together. So this is one way of representing your data, but it's kind of hard to figure out what's going on over here. We can see there's some zeros, there's some high numbers like 53, low numbers, but are they really high, are they really low? Is there any grouping here? What's going on over here? It's hard to see. So this matrix would be the foundation for all of these social analysis we're going to use from now on. But to start looking at any pattern here, we have to test this null hypothesis. So for now we have we see some variation in association index. Some pairs with higher values than the others, but is that really an indication of any structure? Or is this variation just by chance, or sampling artifacts? Perhaps some individuals are more easily to be identified, so you're gonna see them more often just because they are always there in your study area. Or some observation biases. If you're using photo ID, for example, some individuals are super easy to identify and others are not, so there's some individual variation in factorability as well. So to have, we're going to have better conclusions about this when we consider a reference. And our reference here would be what would we expect by chance. So we want to see right now what's the new expectancy for this association matrix. So if there's any structure in our association matrix or any social structure, one basic condition will be individuals do not associate at random. So they just don't form a group with whoever they find in the first place. So it has to be some sort of preference. I want to be with individual B, individual A, or even Joseph, that is the most popular guy so far. So the first new hypothesis that we want to test is individuals do associate at random. Just form groups with whoever they find. And so that means, in other words, that the association index, they're not different from what we would expect if individuals just associate by chance. And our goal here is try to disprove or reject or nullify this new hypothesis. If that's the case, if we can do that, then we can move on and start looking at other patterns in our data. So to put in more formally, our new hypothesis would be individuals associate at random. And so that means all the association indices, they are similar. We can see, just looking at our matrix, that there's some variation. There's some zeros, there's some 0.3, there's some 4 point something. So there will always be variation, but how much variation we need to say these two guys over here, or this group of individuals here, they're particularly high, their association index are particularly high or particularly low. So our alternative hypothesis would be that individuals do not associate at random, but their particular pair of individuals, they're seen together more or even less than we would expect by chance. So we want to see an expectedly high association index, and that's an indication of preferred association. So if I always choose to hang out with one of the Ryans, for example, then if someone is sampling us, is looking at our grouping patterns, over time, we always going to be in the same group, or most of the time. So we want to see if that proportion of time is higher than I am associated at random with, I don't know, Enrico, for example. And same for low association. So if our association index is unexpectedly low, then it might be an indication of avoided association. So I really don't want to hang out with Enrico. I always avoid him. So most of the time, you're not going to see us in the same group. So just a note on statistical inference. There's basically two ways. The most common one is the frequentist. So we try to draw conclusions based on a statistical sample. So basically, it's the classical hypothesis testing that we have. We have a null hypothesis, an alternative one, and we want to nullify or disprove the null one, and then we have evidence for the alternative one. So an example would be reject the hypothesis that tomorrow will rain. Here in Halifax, I'm sure that's not true. It's probably raining right now there. And then another way of looking at this is a Bayesian approach, which is philosophically different. So we have previous knowledge about our system, which we call a priori distribution, and this is updated by the empirical data. Then we go there and collect some data, and we generate a new knowledge state, which is a posteriori distribution. And this is it. So with our example of the rain, here the kind of information I will have is there's a 10% of chance of rain tomorrow. So there are different ways of looking of things. We're going to focus on the classical one here. So Bayesian is beyond the scope of this course. So the frequentist inference. So this is the basis for any statistical test, either parametric or non-parametric. So we have a distribution here. It could be a theoretical distribution, and we have different regions on that. So the rejection region. So if our observed empirical value is in this region here or here, then we can reject a null hypothesis in favor of the alternative one. And on the other hand, if our observed value is in this non-rejection region here, we do not have evidence to reject a null hypothesis. So it's kind of tricky way of, tricky wording, but that's more or less how we see. We're not going to say one is right, the other is wrong. It's more like we have evidence to reject a null hypothesis, or we do not have. So there's several critics for this approach, but still alive, we can still use it. It's just one way of looking. Some people will argue that the Bayesian approach is much better or superior. I think it's just different. They're both advantage and disadvantage. I'm gonna stick with this one. Just remember, I'm sure you guys have seen this many times in your life, but here's the two things that we want to do, the right decision. So if the null hypothesis is true, what we want to do is be failing to reject the null hypothesis. And if the alternative hypothesis is true, we want to reject the null hypothesis. So we are always working with the new hypothesis. In our case here, that individuals associate at random. But we can commit errors all the time. So the wrong decision here would be the false positive. Which we call alpha. So the test, in our case, this test will suggest there's a pattern when actually there's no pattern. So there's a social pattern when individuals actually associate at random. So that's one error we can commit. And the other type of error, type 2 error, is a false negative. So, the test does not suggest a pattern when it's actually there is a pattern. So individuals do display social preferences or avoidances, but we are not able to detect that pattern. And that's what we call beta. And so failing to reject a null hypothesis when it should be rejected, it's what we call beta, the type 2 error. And the statistical power then is 1 minus that beta value. So it's the probability of detecting a pattern when it does not exist. Just to give you a better example of this false positive and false negative. So here's a case where you type 1 error, so you detect a pattern when there's not. Maybe there is, and here's the other way around. So there is clearly a pattern here, but we're not detecting it. So we want to avoid these two things, especially male pregnancy. Avoid that. So we, for the parametric and non-parametric tests, we always use a distribution of values as a reference. So it's based on these theoretical probability distributions. We have many types of them. The normal distribution, log normal, Poisson, and so on. It depends on the type of your data. You can compare with different theoretical distributions. But to use this as a benchmark, we have some assumptions to meet. But this is not always the case. What happens when the assumptions for these distributions do not do not hold for our case, which is probably
So you're trying to.
which is usually the case for our.
Sorry, I just something like because see what you write as a reference now.
Oh yes. Maybe you're a little bit closer.
Sorry, I just.
No, that's fine.
One less.
Sound great. Better.
There you go. Because there's useful references at the bottom.
Oh yeah.
So
I don't know what I'm gonna. Okay, let's leave it like that. Okay, so to use those theoretical distributions, we have some assumptions to meet, but that's not always the case. And for association matrix, we will not, very likely not meet any of those assumptions. So what can we do instead? So we go ahead and create our own distribution. And that's the basis of a new model, for example. Our goal here is to compare our empirical results, so our association matrix in this case, with a new distribution generated at random. So we're going to use our own data to create our own benchmark distribution. Does that make sense? Really?
are you surprised?
So if you don't have a theoretical one, we go and create our own. But not a completely random distribution. We could just shuffle our data at random and create a totally new distribution. That's one way of doing it. But the more features of the empirical data we retain when shuffling the data, more statistical power we will have. So deciding which features of the empirical data to constrain and which ones to randomize is actually the art of building your new model. So what we want here is create a null distribution that we remove the influence of a given mechanism. I'm going to show you more. So, but at the same time, we're going to keep some biological features of this data set. So completely random, just a definition of random, something made, done, happening, or chosen without method or conscious decision. It's not the jokes that I'm trying to apply here, nobody's laughing. It's not random, it's just meaningful communications. So we could compare our association matrix with a completely random matrix. That's one way of doing it. But the statistical power for this will be very low because we are comparing something that we know is not 100% random with something that is completely random. So the chances are we're going to reject that null hypothesis. We're going to commit one of those two errors. So again, the art here, our goal here is to create a null distribution, but also constrain some important features of the data. So the new distribution is going to be based on our own data. We have to choose one metric or statistic or parameter as a reference. We're not going to compare the association matrix itself. We're going to compare one summary statistic of this association matrix with this distribution of summary statistics of many randomized matrices. Does that make sense? Yes, yes. I don't know what you're talking. Yes or no? Have you guys seen this before or heard it? Good. So we know what's happening. Good. So usually we create lots of new matrices 10,000 to 20,000 or even more. And then we create, each dot here would be one value for a random matrix for our chosen statistic or metric or parameter. Then we plot this distribution here, and then we have the confidence intervals, and then we can look at those rejection areas and non-rejection areas and see where our observed statistic falls into here. So here for illustration purposes, I put here as it looks like a normal distribution, but it could take any shape, it doesn't matter. So again, this is going to be is the same for the frequentist inference, but our distribution is null, and it's our benchmark. It's not one of those theoretical distributions. So we just need to choose the alpha, a value for the alpha, usually 5%. So we have 2.5% on one side, 97.5% on the other side, and then we look at the proportion of null values. They are greater or smaller than the empirical value, and that's our famous p-value here. Good, but how can we do that specifically for our association matrix? How can we test if that beautiful association matrix is just random or not, or if there's any preferred or avoided association? So we're going to use what we call the permutation test or randomization test or exact test. Have any of you done this in the past? Yes, yes, no, yes, really. Good, great. So essentially what we're going to do here is we have our raw data, individuals in groups, and we're going to shuffle them, put individuals in different groups and calculate association matrix, then shuffle again, calculate another one, do this 20,000 times, and each time we're going to calculate one summary statistic. It could be coefficient of variation or the mean association value, depends on your question, and then we're going to compare the empirical one with the new one. So it's a statistical test. So the distribution of the test statistic, it could be, again, we're going to see this better, the coefficient of variation or the standard deviation or the mean or of our association index. This could take any of those. So it's calculated, it's obtained by calculating all possible values under rearrangements of the observed data. So this is what is permutation per se. And this permutation, one way of doing it is the so-called Monte Carlo permutation test. So we're going to shuffle the matrix element. This is what. We're going to shuffle the matrix value, and there's different ways of doing it. We can just shuffle at random. We can without replacement, and the matrix that we're going to the new matrices we're going to generate, they will have the same dimensions of the observed one. So we can either do this on the raw data, on the group by individual matrix, or on the association matrix. So the original procedure for this uses what we call the pairwise swapping algorithm. So we go to our original data matrix. Remember this from yesterday, just to remember. Here we have groups and individuals, so this is our variables, our samples, and the presence is individuals in the same group. So here we have, first group we have individual A and B, and C and D actually. Group 2 we have A and B, and here we have just individual B alone and so on. So this is the raw data. What we're going to do here is shuffling this, but in a specific way. The way the algorithm works is we go, so he comes here and you're going to select 2 columns at random. But these 2 columns, they will form what we call the checkerboard pattern. So we were looking for 2 by 2 submatrix, and it has to form this checkerboard pattern over here. So here we select these one and these one, and here. So we have this pattern over here. So we find this submatrix here, and in the next step, what the algorithm will do is just flip this. So now, what it was a 1, now it's a 0. So we actually flip this little matrix. Now we have a 0, 1, 1, 0. So this is basically how the algorithm works. And there's a reason for why it's exactly like this. Let's see. And we do this 10 to 20 times, 20,000 times. So every time this original one, it finds this pattern and it flips. And in theory, this is a new matrix, but obviously it's super similar to the previous one. But anyway, we're gonna fix that later. But for now, this is just imagine that this is how it works. And the reason why it is like that is because by doing so, we constrain here 2 very important features of these data. So if you remember, the sum of these columns here gives us the group size, right? So here if you have in group 1, if we have individual A, B, and D, we have 3 individuals. Here we have 2, 1, 3, 4. And here in the column, so this is row sums, then the column gives the capture. So individual A was seen 4 times, B was seen 4 times, C was seen 2 times. So by doing this flip here, look that these guys are different. Everything is the same, but this is 2. Do you see that we flip this? Is that good? So when we flip this way, the group size and capture frequency is maintained on the randomized matrix. So what we're telling here is these 2 are very important biological features of our data. If these guys seem only 4 times, there's no point of comparing our real data with null data when these guys seem 40 times or 15 times, for example. This is not what actually happened. And if the distribution of group size is usually from 1 to 4, there's no point in having a matrix where a null matrix where you have groups of 17 individuals. We never see that, so that's very likely not the case. So this is a way of constraining our permutation and making our statistical tests more robust. So we have more statistical power. Any questions on that part? No? Very clear?
Yeah. Maybe I missed it. Because there you have 1, 0, 0, 1. If you have 1, 1, 0, 1 and you do the permutation, then the order of the sum would change,
Yes.
wouldn't it?
Yes, but that's one problem of these algorithms. It only flips this checkerboard submatrix. So it will only work when you when you find this type of thing.
Okay.
Or this, right?
Yeah.
When you find these two cases, this is the checkerboard. So if it finds something like this, as you're saying, it will just keep that. And that's one limitation of these algorithms. And we're going to see there's some criticism to this way of permitting your data, but there's other ways of getting around this.
Yes. If
Can you go there?
with the number of permutations, does
Yes.
it just go like, for instance, this is a really small data set, but does it just take one, flips it over, and makes a new one? Then it goes back to the previous one, makes another one, and adjusts that, or does it go for the second one? Because if you look at the second one, there's another. It creates another checkerboard.
That's right.
So will it take that one and continue on, or because the numbers stay the same in the end, the columns?
Yes. So that's another criticism that people have raised on this type of algorithm, and the way they figured that. So you always start with the original one, but if you do just one flip, it creates a very similar one, and then you go back to this and you find just one more flip. So at the end you have a distribution of no matrices. They are not actually that different from the original one. So another way of getting around that is you take your original one and you do not just one flip, but a bunch of them, usually 1,000 flips. So in the first step from here to here, you're not going to look just for one submatrix. You're going to look for 1,000 of them, and then your next one it's likely to be much more different. And then you.
That's the second set that you work on. Yeah.
Yes. Then so here we're just doing one flip. So nowadays the way you do it, you do 1,000 flips from here to here, and then you go back and do another 1,000. But obviously in this case it's hard to even find this. But if you have a bigger matrix, that will make more sense. And that was another criticism. And I think there's a slide explaining a little bit more about this. I'll go back to it. So what these algorithm constraint is. So we're going to constrain the capture or observation frequency, the column sums, the row sums, which is the group size in our case, the number of individuals, which is the number of columns, and the number of rows, which is the number of groups. So we have always the same dimensions, and the total observations, so the matrix field, which would be the sum of all ones we have here. 13, yes. So 13. So we're always going to have, in this case, 13 ones and zeros. So we're not putting more ones than you've seen originally and then taking them off. So it's a very, restricted way of permitting your data. So it gives you good statistical power for that. Now, the criticisms, one of them is you always select, you always look for these checkerboards. So the algorithm, it's supposed to be random, take 2 random columns and 2 random rows, but not always you have the pattern. So we always go for the columns and rows that give us these patterns. For example, in this case, if it selects this guy, this, and this, we don't have the pattern. And so the original algorithm will just skip that and look for another one. But that could create, and usually does, a biased distribution. And some argue that this effect is small, blah, blah, but now there's this was already corrected with the with this correct Markov chain Monte Carlo. So what actually means is, even when you find this situation, it keeps that matrix as well. It doesn't flip. So this is what they call waiting steps or trial swaps. It's also part of your null distribution. So you're not, if you don't do that, it's likely that you're going to have a biased null distribution because you're selecting for the columns that you can do the permutation. Does that make sense? Any concerns about that? So the idea is, if you don't find it, you keep that way that one as well. And that's why it's important to increase the number of interactions to 20,000, for example, so you can try all the possibilities. So yeah, when there's no checkerboard matrix, that original one is kept in the distribution. So yeah, some problems with independence. That's more or less what we're saying. So if you always do one flip after the other, at the end we're going to have a distribution of null matrices that are way too similar to the others, and one way of getting around is flipping 1,000 times each time. Another problem is demographic effects. So if you have a huge study, for example, 30 years in her case, then if you have a, this is our matrix again. So say these you collect this in 83, and this, I don't know, 20 years later, and well, you got the point. The idea here is, if you have different sampling periods and you put all of them together, it's likely that you have a demographic effect. For example, these guys were here in 83, but this one is alive, but these guys are not. They might be just dead. So there's no way you could possibly interact with these guys that were not even born and were born in 2003. So that means when you don't consider the temporal scale of your study, you are flipping individuals that never had the chance of associate. So it will come up with they were avoiding each other when in fact they never had the opportunity to be friends, and that's pretty sad. So you have to consider that. So the individuals are not in the same space at the same time as are mistaken as avoidance. And that's the problem. And one way of getting around with that is defining smaller sampling periods. So we can do, I don't know, like 6 months or a year, a period of time that in your case is biologically reasonable to define the population is closed. So if your individual lives 50 years, for example, maybe 1 year, it's unlikely that there's many births or deaths or immigration. So the smaller your sampling period, more robust your test will be. So it depends on the taxon. If you're, I don't know how many years a bird live, maybe 4? I don't know. I have no idea.
Our species can go up to 16.
16. All right, good. That's happy news for me. I thought it was just 4. Okay, but I don't know. Maybe if you're working with invertebrates, I have no idea. You have to adjust that to your the taxon you are studying. All right. So let's do the two. Any questions? Yes.
Yes. When you say to do the 1,000 flips instead of doing one, maybe, I don't know, depending on the sample size and what you see, there's no chance for 1,000 flips. So is there like some sort of rule of thumb depending on the amount of checkerboards that are in your data. Like I don't know if there's only 1,000 flips available. Obviously, when you do 1,000 flips, you're already like you will have the final one already. There's no other possibility. So I don't know if you have 1,000 flips, maybe it would be better to do like 100 at a time or something.
I see. Yeah, that's a great question. I actually never thought about that, but I think if you do 1,000 flips, you redo the other flips as well. You know, if, for example, say you have actually 50 checkerboards on your small matrix,
Mhm.
you will keep doing flipping and reflipping those same ones. So we just shuffle a lot. Just like,
Consider it up to 1,000 flips.
yeah,
Oh, okay.
yeah.
So
If it doesn't have the chance to do, I think what is gonna, if it's similar to other kind of permutation, is we will redo the same
Yes.
until we reach that one. But in that case, it wouldn't consider twice, it would just
Okay.
Yeah, maybe in this case here, I don't know, this one will flip and then reflip again and then flip the same again. You see what I mean?
Oh, so it does like different combinations even. Okay.
Yes, I think
Okay.
that's, but I will look it up. I actually never thought about that. But yeah, it would make sense if you have a smaller matrix, then you don't need that much. It's just 1,000 is just
Just like
arbitrary. Like
Okay.
it's-
But I guess it does depend on like the observations that you have, because if you don't have 1,000 like of
That's-
these checkerboards, then you can't do it.
That's a great point.
Okay.
And the way it's set up in Sockprog, for example, you can adjust the number of
The
flips.
number of flips.
It's
that you
just
do.
like 1,000 is the default
That's
value.
why
but
I was asking if there's like a rule of thumb depending on the data that you
I
have.
see.
I don't know, 10% of the amount of checkerboards that you have, or like 20% the amount of checkerboards that you have.
I'll definitely look it up. That's a great question.
I think this is one of the things that biologists don't ask.
Exactly.
They just accept it. It's like age in
That's
home range analysis.
Yeah.
Nobody knows what it is. Okay.
So in Sockprog we have 3 options for meeting our data. I'm using the original, the name that is in Sockprog, but this is the same as a classical Monte Carlo test or exact test. In Sockprog it's called permute all groups. So this is the original one. You will just take your matrix and do those flips, and it could be biased by demographic effect, like I said, if you don't consider the sampling periods. And the other one is permuting groups within samples. So it's that way. If you know your sampling periods, you will only make the permutations within that chunk of matrix. So, well, I'm gonna show. There's a slide to explain that. And it allows us to test long-term and short-term association. And I'll get back to this, but by long it means between sampling periods, and by short within sampling periods. So if your sampling period is a day, a long term association is between days. It's not that long, you know. But if your sampling period is a year, what it means is it's testing between the sampling periods. So don't take long and short too seriously here. It depends on how you define your sampling period. Yes.
Sorry, on the bias of the demographic aspect, that's the temporal aspect. What about, I don't know whether you already talked about the spatial aspect. For example, Erin was saying that she's got different location where she gets her photos.
Yes.
So if an individual is here, it cannot be here and there and there.
That's right.
So there's not an equal chance, also spatially, not only temporally. Is it something you...
In this case, I think I would. Let me see. You could.
Or Ryan case, in case of
Yes.
the white shark, we looked only in one location. But if we looked at different locations, obviously there would be a similar problem. They cannot be everywhere. So
Yes.
it's not completely random.
In this case, I would run the test for each matrix of each location. If you know there are different locations and they're very likely to be especially segregated that way, I would not even put them in the same matrix. That's one way of doing it. The other way would be adding a factor like the sampling period. You you will add a different category here. So if you have, you know, if you have your matrix here, and this is, I don't know, site 1 and site 2, then you can make the permutation run only within this and within this,
Okay.
right? Instead of being the time. And I don't think you can do that easily in SockRock, but you could do that in R easily. There's a, you just, yeah, you just put a different categorical variable there. But yes, that's another, so this asocial factors like time and space, you always have to consider them, otherwise you're just biasing everything. And a third way of doing this permutation, we're going to go through all of them in a minute, is in SockRock called a Permutation Association within samples. So what is happening here is, instead of flipping the group by individual matrix, we're flipping the association matrix itself. So you have the binary data with individuals and groups, and then you calculate the association index, and then you have the association index, and you flip that one. And that controls for gregariousness. We're going to get back to it in a minute. But it only tests the long-term associations between sampling periods. I'm going to go through the 3 of them with more details, don't worry.
Okay.
So the first one is permuting all groups. So what we do here is shuffle the whole thing using the flipping, right? Selecting this and 2 columns, 2 rows. If it's a checkerboard, flips. Do this 1,000 times, and you create 20,000 new matrices and calculate association for each of those, and so on. So we constraints, as we said, group size or sum of the rows, and individual capture frequency, sum of the columns. But it does not account for this demographic effect. So individuals are not there because of birth, or are there because of birth, death, migration, etc. It does not account for gregariousness, which is the tendency of some individuals to form larger groups than the other. This guy here is seen alone, and A is always seen in larger groups. It does not account for that. It's recommended for short and small studies. So if you are in a small area with few individuals for a short period of time and you can see them all the time, you might as well flip the whole thing. So in captivity, if you have 12 chimps in a cage, unless you shoot one of them, they'll probably be there for a month. You know, so even they all have the opportunity to form groups with the other in that specific space and during a month. So if the population is closed and they all use the same area at the same time, you might as well assume that they could form different groups. So that's fine. Go ahead and flip the whole thing. Yeah. And so it does test for short and long-term associations, which again, I'll stress that again, short means within sampling period and long between sampling period. And in SockRock, you can do that only if you define a group. If you have your data into that group mode, or in a linear mode, but you know these 3 rows here are group 1, group 2, then you can do this. So the second way of doing in SockRock would be permute groups within samples. So we first define sampling periods, and we're going to do the same thing that we do, but within those sampling periods. So if this is a day, so we're going to flip only within a day. A day is usually too short for pure. So maybe a month, 6 months. So I think in our case we use 6 months, I guess.
When we tried that, then we switched to days.
2 days, yeah. Yeah, it depends on your study, really. This is something that we have to think really carefully according to the study you're using. Yeah, so the permutation is restricted here to to remove the demographic effects. It does not account for gregariousness, so if individuals are found in small groups or huge groups, we do not account for that. It's recommended for long-term studies, so 30 years of data, or 10 years, or even 3, 4, depends on the lifespan of your study the object. And it tests for both short and long-term periods. So for preferred associations only within this block of time and between them. So long-term would be between, short-term would be within. And again, in SoccerProg, this is possible only when you have these type of data, individuals and groups. And the third and last way of doing is flipping the association matrix. So from this guy here, we calculate the association matrix. Now, if you look, I don't know if you can see, but now, yeah, we have this association index here. So it's a symmetric matrix again. So we have individuals by individuals, and it flips the associations between individuals. It's a different way of doing. And you can also add the sampling periods if you want, and if you want or not. But the only thing you can compare here is the mean value of the association index. So you only test for long-term associations. And that's what we've done for the white sharks, actually. Good.
Do you flip it including the diagonal value?
No, it's diagonal. There always be one.
So
Yeah.
just one side.
Yes. Yeah. Yes. Yeah. You flip just one triangle. If you have, you're gonna see this, I think tomorrow in the lecture on new models. Another way of doing this is creating a agent list. So you have like A and B, A, C, A, G, and so on. And then your values here, and then you just swap them around. So basically you take this triangle here and transform in a list, and then just flip these things. It's the same thing.
Can you repeat, sorry, the test part?
This?
Yeah. Why only
Oh, because so the mean values here will be always the same because we're just changing the values around. And
yeah.
I'm gonna show in a minute. The way we test short-term associations is comparing mean values of association index. And in this case, the mean value will always be the same. So there's no way we can test that. So in the way we test for long term is looking at coefficient of variation. I'm going to show you the next slide. So, okay, so restricting permutation within sampling period is a good idea if you have a long-term data, but how long it depends on your study. If it's too short, you're going to have just a few groups, and your permutation will be so restricted that you have small power, little power, statistical power, and often a degenerated matrix. So we might have that problem that in SoccerProg. What it means is you have, if this is too small, for example, and you have two groups, you do not even have a submatrix here that has a checkboard. So that would be, you're gonna end up with something. Yeah, maybe you have just, make this easy. If you have one row, you not even have a submatrix here to flip. So that will give you that problem of degenerated matrix. So then you have to increase. Then you have to increase the sampling period. But if it's way too long, you might have the demographic effect, and that increases our chance of committing the type 1 error, which is rejecting the null hypothesis that individuals are associating at random when it's actually true they are associating at random. So we have to try to be biological, as close to the biological picture we can get. And one way of looking at these patterns is using lagged association rates. We're going to see this in 2 days from now. And we can get back. We can study the temporal stability of the associations and try to find a natural break. And also after more or less 6 months, they tend to die off. So maybe 6 months is a good chunk of time. And okay, so I said that we have to create a null distribution of values, but which values, which statistic? You're going to create 20,000 random binary matrix and then 20,000 association matrix from those. But we're not going to compare the entire matrix. We have to find a statistic to summarize the entire association matrix, right? So we can use any of those guys here. We can use the mean value, the standard deviation, the coefficient of variation of the association index, or do the set of the proportion of non-zero association indices, or all of this only from the non-zero association index. So what I'm saying, once we have that association index here, matrix, we have the original one, and we have 20,000 of those. So we could calculate just the mean association index here and the mean for all of those. So then we have, say, we have a distribution of 20,000 mean and our empirical value over here. You see what I mean? So we can choose any of those statistic here to calculate either in the empirical one and the null ones. Okay. Any questions? Good. But how are we going to choose them? It depends on your question, right? That's what always people say. When you don't know the answer, that's usually the best thing. No, it depends what you want. Of course it does. So it depends. So we have, to make it simpler, we have 3 options here. We want to see if there are long-term preferred or avoided relationships. We might want to see if they're short-term preferred or avoided. Or you might want to see if there is gregariousness, if there's individuals found in larger groups or smaller groups. So depending on this question you want to choose the right statistic here. So if you want to look at long-term relationships, the one statistic that we can use is either the standard deviation or the coefficient of variation of the association index. So many Asians. So again, long-term means between sampling periods, and preferred or avoided relationships means very high or very low association index. I'm just translating like the nice biological interpretation of it to actually what's happening in the data. So we're just looking between high or low values of association indices between sampling periods. And the standard deviation and the coefficient of variation, they are measures of dispersion, right? So if you have a very uniform distribution, how is that? So if you have a distribution here, and it's more or less, I don't know, uniform, so there's not much variation here. So that means either if all of your association indices, they're either low or high, doesn't matter, but there's not much variation. You don't have, if you plot all of them, you don't have, not even, you don't have a pen that works.
Yes,
That's
right.
what you, it's because it's wet.
Yeah, by the book.
Yeah, no, it's because this
Ah.
thing is wet. I'm just gonna wait a little bit.
I can get you.
It's alright. Here's what happens. So, coefficient of variation and standard deviation is a measure of dispersion. So if you have lots of zero values and lots of 0.8, 0.9, so you have a lot of variation. That means you probably have small association units and high association units. So if you have that means you have a lot of variation in your data. If you have a small standard deviation or a small coefficient variation, all of your indices are more or less the same, 0.2, 0.3, 0.25, so they're not much variation. So if there's a lot of dispersion in the data, that means that we have unexpectedly high or low association indices. So probably we have preferences or avoidance. Oh, great.
Doesn't look good. Wasn't used approach.
That's usually the requirement for this kind of things. So, is that clear? Does that make sense? So I'll just repeat a little bit for you. What we're testing here is if there's a lot of variation in your data or not. If there's a lot of variation, a lot of dispersion in association indices, that means in our data we have some indices super high, some super low. So we have probably some preferred and some avoided relationships. So if you want to test for these kind of things, CV and SD are a good way. Just remember the coefficient of variation is nothing less than the standard deviation divided by mean. So it's the same thing. So we're testing for variation in the data, or dispersion in the data. Now, if you want to test for short-term relationships, you might want to see the mean value, either of the association indices or removing all of the zeros and looking only at non-zero ones.
Mauricio,
Yes?
what's the practical difference really between using the AIs or only the non-zero AIs?
Good question. I think it's just, let's see, if you have a lot of zeros, a lot of association indices there are zero, you might have more chance to find avoided relationship when in fact they were never seen together or in the same area. So I think removing this, we're gonna look only at the mean of the realized associations. I think it just makes a little bit more restrictive.
Yeah.
I think it also increased type 2 error because when you permutate and if you have a lot of zero, then your matrices are going to be a lot alike.
Yes.
So when you do the multi-color permutation test, you have more chance to find a pattern that is not there, just because you have so much zero in your data that
That's right.
the permutation test is not going to be, actually it's not going to make sense. And that's why I wanted to ask you this question that I can teach for myself, but if you have any literature, you know, that rule of thumb of the number of missing value or non-zero or like zero association index that you should have in order to, or not have in order to avoid detecting pattern not there. If you have any literature on this, because I know that the more zero association index or missing value you have in the matrix, the more you can increase the zero of seeing pattern that is there. So if you have any paper or any sort of your personal experience on this, to discuss, I don't know if there are other people that are interested in this, but otherwise we will chat about it.
Sorry, if you have way too many zeros, what is that word? I think I kind of lost your
Threshold.
Mm.
Yeah.
Yeah, sorry. So in a matrix, in an association matrix, or in an interaction matrix, in that case, it's going to be like missing value. That interaction you have an observed between two individuals.
Yes.
So the more you have of this zero association index or missing value, sorry, the harder it's going to be to get clear, unbiased result from your Monte Carlo permutation test.
Yes.
Yes. You follow me there?
Yes, yes, yes.
So I don't know if there is any rule of thumb that tell you that, yeah, if you have that many individuals and you observe that many interaction, you should not have more missing value or more zero association index, because otherwise it's going to bias you estimate from Monte Carlo permutation test. So I don't know if you experience this, but this is something I experienced in my case.
With the associations, I think one rule would be removing individuals that were seen interacting lasting 3 times, like we did yesterday, lasting 5 times, for calculating the indices. That's the only thing I can think of right now. But the interactions, I'm not quite sure. But,
All it does is, yeah, just that the
Okay,
question
yes.
related to my question, but if we can chat about it.
yes, for sure. I'll think more about it. But for now, I would say removing these individuals that we're seeing just 1, 2, 3 times, like just a few times, because that will actually bias the calculation of the index. They will be seeing, they will actually be pretty, they'll have no interaction with anybody else, but not because just because you haven't seen their interactions, right? Not because they choose to be alone, for example. So usually, yeah, that's why you need a lot of data, and they focus on that core of individuals that you've seen a lot. So the only rule I can think right now is removing these individuals seen at least less than 5 times, for example. But we can talk more about that. Okay. Let's see. So in this case, let's see. So if the average association index is significantly low, there is preferences within sampling periods. So if you want to test for short-term relationships within sampling periods, the mean association index is the parameter you want to choose. And then for gregariousness is a little bit different. So here what we're testing is if you have individuals, they're consistently found in larger or smaller groups than the other. So our new hypothesis here is a little bit different. Individuals do not differ in their gregariousness. They have a typical group size. They always have more or less, they're always found in groups of 7 or 6 or whatever. And that's wrong here, should be alternative hypothesis. So given the individual gregariousness, the pairs of individuals do not differ in the rates of associations. So if you want to test for that, we want to just look at the standard deviation of the typical group size. And in Socrates, if you want that, it will spit it out for you. So that means if you have gregariousness, you're going to have a high standard deviation of the group sizes, which means you have a lot of dispersions. You have super big groups and super small groups. And to do that, we can choose this option, permutation for gregariousness and soft drop. I'll show you how. Let me see how much time I have. Yes.
For the long term, the first one that we saw. So if we do the association index or of non-zero AI, doesn't that kind of get rid of the problem of the demographic stuff? That like, so if, because we're going to have a 0, 0, if like they have never had a choose because one is it and one is not. If we use the non-zero ones, then we kind of get rid of the problem. So if we are doing the long term, we don't really have to worry all that much about the fact that one is allowed and one is dead because we're removing the non-zero ones.
Yeah,
we're removing the zeros.
That would reduce that. Yeah, that's right. Because then but you're also saying that. Let me see. So when you have a 0, it could be either they never interact because they don't want, or they
Yeah.
were never seen together, or
Yeah.
they were never there, right? So removing the zeros, you take all of that possibility and then you look more. Yeah, I agree with you. You remove a little bit of the demographic
The
effect.
demographic side.
Yeah, but I think I would say a better way of removing would be
Just
doing
do
it
it with like short stamps.
yes.
Because then you don't have you can look at the avoidance.
Yeah.
But then I would never want to use the association for the, like removing the zero, or zeros. So I would never use like the B of the options.
The B? Sorry.
Like, so I would never use the second option of using either
The
just
non-
SD or the CB for the all the non-zero.
Yeah, you can still use it because, I mean, even removing the zeros, you might have like 0.3 or 0. As opposed to 0.9, you still
Okay,
can
so you're
see the
still
variation.
having the avoidances because it's not
Yes.
just zero, it's a 0.03.
Yeah, it will be lower than
Okay.
expected, but they might one day hang out just for a day, for example. And
Okay.
avoidance doesn't mean like at all.
They don't
It's just it's
do it at all.
smaller.
So I
Yes.
guess it does get rid of just the fact that they're not at the same time.
Yeah, it reduces for
Okay.
that as well. Let's see. Okay, so just so if we reject this overall hypothesis that individuals are not associating at random, or reject the null hypothesis that they are associating at random, so they are not, then we can extend the test to look at each individual. Then we can test. So this guy over here, Joseph, and I don't know. You just see, actually, one look better names now at this point. So these two guys prefer they prefer to associate with each other or not, or they avoid each other. So it would be the same idea, but now we move from the population level to individuals. So we can look at the end. All right, they do not associate at random, and these are the guys who prefer themselves, and these are the guys who avoid themselves. So we can look at that. To do that is the same whole idea, but we just need much more interactions. So usually more than 20,000 interactions to have more statistical power. And so we have to, just a word of caution here. So we're gonna have, I'll show you an example. 2 individuals, their association index, and if this index is significantly high or low, and we'll give you a p-value for that. So just don't use the p-value as a measure of how strong they are. The measure is actually the association index. You just say, oh, this is higher or lower than expected. And to summarize some recommendations. So if you want to look at long-term preferred or avoided companionships, you're going to look between sampling periods, and we look at CV or SD of the real association index. If you want short-term, you're going to look within sampling periods, and we're looking for the low mean values of the real association index. So we want, here we're looking for high values of dispersion. Here we're looking for low values of mean. And in differences in gregariousness, you're looking for high values of variation of the typical group size. Quickly, an example here. This is for the bottlenose whales. It's a type of big whales, the deep divers. They are pretty much in the middle of nowhere, and they're found off Nova Scotia in Canada. So the males, so here only for the non-zero association index. So the real standard deviation is 0.1, and the expected is 0.09, and this is significant. So here you're gonna, it suggests that the males, they do not associate randomly, and there's some preferred groups. For example, these 2 guys, the A24 and the 118, their association index is 0.7, but for this system, it's a quite high value for this system. Now, when we look only for the females, the real association, the real standard deviation of the real association index is 0.09, and the expected value is pretty much the same, and it suggests that there's not much variation here. So the females tend to associate randomly. Good. So,
Sorry.
sure.
So for the males, now we know that it's not random, but do we? No, maybe my question doesn't make any sense. Never mind.
Okay. Let's see.
Yeah.
Any questions? So we can, let's see, we have about 10 minutes and we would do all of this in Stockbrook. Let's see, maybe we could,
Can I ask you a question? Unless you have to something else just to fill time.
No, we have-
Have you finished this
yes, but there will be the practical part which might take a lot of time.
in the next 10 minutes?
Well, it will take maybe.
Okay, I'll carry on. I'll
Oh,
ask
we
you a
can-
second.
No, we can ask, we can.
Again, a slide before.
This one?
Before. Yeah.
This?
You're looking at short-term preferred, for example, the second one, short-term preferred or avoided companionship. Why the mean is low?
Yes. Let me see.
I could understand for avoided companionship we have a low mean.
I always get that confused. Just give me a minute. I'll look it up my notes here.
The same thing with the others. But no, the last one is fine. The previous one as well. Why they? Because if it's the short-term preferred.
The average association. I don't remember right now. I'm not gonna lie. I'll look it up and get back to you.
Because we're testing basically for non-random, right?
Yes.
For random, basically, and if it's rejected, it's either preferred or avoided. Now,
Yes.
a mean association index low, maybe I skip some, I miss something, I would expect an avoided relationship. Am I
Wait,
wrong?
we're comparing short term, so we're comparing two lines, for example, right? So we want
Yes.
those two lines to be similar. So that's why
Yes.
we want a low mean. Because if those two lines are similar,
That's
then it
right.
means that those companionships are kept, either avoided or
That's right.
the companionship. So we want those like sampling. So I don't know if we have like first line is 1 day, second line is day 2. We want day 1 and day 2 to be similar. So we want a similar mean, a low mean, so that there's like a small difference in
That's
between
right.
the two
Yeah,
lines.
that's exactly what it is.
So that means that those groups that are seen together are kept consistent
Exactly.
in between sampling, in between days, in between sampling periods.
Okay, so the
Short term is within separate.
Yes. Yes.
Yeah, so
So
you're
there's
comparing
no-
one line and the other
Yeah.
line.
So it doesn't very much within.
You go out for a couple of days within rotation too.
I think that's.
Is it?
Yeah.
The percentage
Yes.
of 2 days and then 2 times.
And then like 6 months later, then you expect
So within the permutation, after the permutation, that's what we're looking.
Sorry.
After the permutations, we look at the mean of the different results. Is that what you say?
Yes. Yeah. So you're gonna compare the real mean
Yeah.
with the mean after permutation, right?
And so if it's low, means there's not much difference.
Yes, it keep, within that sampling period, it keeps more or less the same. So,
Okay.
This is
Okay.